Hello, myself Mohammad Hurs Khan of CSE ANML is here to give a presentation and my topic is jump search algorithm. What is jump search algorithm? Jump search algorithm is a relatively new algorithm for searching an element in a sorted array. The fundamental idea behind this searching technique is to search fewer number of elements compared to a linear search algorithm which scans every element in the array to check if the if it matches with the element being searched or not. This can be done by skipping some fixed number of array elements or jumping ahead by fixed number of steps in every iteration. Now let us consider a sorted array A of size n with indexing ranging from 0 to n minus 1 and the element x that needs to be searched in the array A. For implementing this algorithm, a block size of m is also required that can be skipped or jumped in every iteration. Thus, the algorithm works as follows. In first iteration, if x is equal to the 0th index, then true, or else if x is greater than the 0th index of array A, then jump to the next block. In second iteration, if x is equals to the mth index, then true, else if x is greater than the mth index of A, then jump to the next block. In third iteration, if x is equal to 2m, then true, else if x is greater than 2m, then jump to the next block. At any point in this, if x is lesser than km, then a linear search is performed. Now, let us consider the following array 0, 1, 1, 2, 3, 5, 8, 13, and so on. The length of the array is 16. Then the jump search will find the values of 55 with the following steps, assuming that the block size to be jumped is 4. In step 1, jump from 0 index to the 4th index. In the second step, jump from index 4 to index 8. In third step, jump from 8th index to the 12th index. In step 4, since the element at the 12th index is greater than the in step 1, it will jump from 0 index to the 4th index. Now, it is starting at in step 4, since the element in step 3, jump from 8th index to the 12th index. In step 1, jump from 0 index to the 4th index. Step 1, jump from index 0 to index 4. Now it is pointing at number 2. Now let us consider. Step 1, jump from 0 index to the 4th index. Now it is pointing at number 2. In step 2, jump from 4th index to the 8th index. Now it is pointing at number 13. Step 3, jump from 8th index to the 12th index. Now it is pointing at number 89. Since the element at 12th index 89 is greater than 55, which is to be searched, we'll jump back a step and come to index 8. Step 5, now we'll perform a linear search from index 8 to get the element 55. By this figure, we can understand that skipping some of the elements in the array and then performing a linear search, we can easily find the required number. Here is the code to implement a jump search. Optimal size of m. The worst case scenario requires n by n jumps and m-1 comparison in case of a linear search if x is lesser than km. Hence, the total number of comparisons will be n by m plus m minus 1. This expression has to be minimum so that we can get the smallest value of m block size. On differentiating these expressions with respect to m and equating with 0, we get an expression n by m2 plus 1. On further equating, we get n by m2 is equals to 1. Finally, m is equals to root of n. Hence, the optimal jump search is root n, where n is the size of the array to be searched or the total number of elements to be searched. Complexity analysis for jump search. Time complexity. The while loop in the above code executes n by n times because the loop counter increments by m times in every iteration. Since the optimal value of m is root n, thus n by m is equals to root n, resulting the time complexity is big O of root n. Space complexity. The space complexity of this algorithm is big O of 1 since it does not require any other data structure for its implementation. Some of the key points of the jump search are: work solely on the sorted array. The optimal size of the block to be jumped is root n. This makes the time complexity of the jump search big O of root n. The time complexity of jump search is between linear search and binary search, which is big O of n and big O of log n.